I
This was an isolated
and
incident.
then I just keep rereading the lines over. So at least I can zoom in like all the way on my computer.
I feel like an old man doing
No,
that.
so like whenever I fully zoomed in and then I have to continue to manually zoom in, I'm like, oh my god. Everyone behind me can see this because it's on the screen.
No, the way I code it, was like really nice. It's 22.
I don't want to see.
No, it's so much.
Can see.
Okay, so, let's kind of start where we picked up. Let me remind you of this exact sequence we had last time. Let me point out that in this exact sequence, so this is the torsion elements, which is a submodule of A. So to do this, I'm assuming the integral domain because the torsion elements aren't always a submodule of A if it's not a domain. But in a domain, we've got this. So this is always a short exact sequence, just doing inclusion and then projection in the natural way A goes to the coset A plus AT, right? Now, in the case that if A is finitely generated, then so is A mod AT. Right? And also, so is AP if we are over a PID. Right, because that business, we need like the submodule of a finitely generated module to be still finitely generated. So if A is finitely generated, you get that's finitely generated. If additionally you're over a PID, then it gets this. And also, now that we've got all these assumptions thrown in here, then A mod AT is finitely generated and it's torsion free. Right? Is it pretty clear that A mod AT is torsion free? Anybody want to see a proof of that? It's not super difficult. I mean, basically, they're killing the torsion there. This is torsion free, and so therefore it's free if you're over PID because it's finally generated torsion free. So the upshot is under the assumptions that we were using the other day. So if A is finitely generated over R, A PID, then A is isomorphic to, this is the torsion module, and this is free. And I'll add a little bit more oomph to it. Of course, the torsion module is finitely generated as well. If F is free and finitely generated. And in fact, this free bit is isomorphic to A mod the torsion module, right? So there's a decomposition. Now, we're going to take apart the torsion module because in a certain sense, this one is easy to understand, right? This piece is just a free R module, so I can tell you what it looks like. This guy, no big mystery here. This is just some number of copies of R. And since it's free, or since it's finitely generated, it's just some number of copies of R. So really, to understand this, all I need to know is what M is. How many copies do you have there? That's it. The torsion module is a little bit more subtle, and so we're going to pick apart the torsion module. And I will review, I know some of you may or may not have seen some of this, so I'll do a couple of examples here. Theorem. Let A be a torsion module theorem, 1317. Let A be a torsion module. And here, I mean, every element is non-zero torsion, over a PID. I'll call R. And let, P be a non-zero prime in R. Let AP, okay, so what do I mean by AP here? I mean, it's everything in A. Such that A it's everything in A that's killed by a power of the prime. Then A is isomorphic to the sum of AP. Its P range is over all the non-zero primes R. And if A is finitely generated, then AP equals zero almost everywhere. AP is zero except for finite limited P.
Would you ever, lower the decibel?
Yes, I can do that,
Thank you.
perhaps. I can also, does this screen get in your way? I can flatten that out too, move it a little bit.
Yeah, that's better. Thank you.
Sure. Okay, so, boom. So basically what I'm saying is everything can be decomposed into, the sum AP. Can you explain why perhaps this is true? Yes.
The ideas are derivatives, and so you, but you're also gonna have, like, you're gonna have a unique factorization into not in irreducibles, and primes are the only irreducible.
I think you're gonna need more than UFD here, right?
More than UFD?
Yeah, I think so. So let's try to prove this. Let's try harder. Let me start with a lemma. Let me make. Well, actually, suppose R A equals zero, where R is not zero. Okay. Suppose that R equals X, Y with GCD XY equals 1. So let's suppose that you could, so far, I'm taking advantage of what he said about the UFD business. Let me point out that, of course, I expect R to have a prime factorization, because if this is a unit, that means 1 times A equals 0, which means A is 0. So I'm going to assume, A is not 0 too, because otherwise 1 kills it, and I'm not that interested in that. Okay. So any ideas what we can do here? Here's something that's true for a PID, but not a UFD. There exists S, T, and R such that SX plus TY is equal to 1.
That's true in PIDs, not UFDs.
It's not necessarily true in UFDs. Now, remember what I'm going for. Well, actually, what I want to do is I want to remember what our goal is. Any element of A, you should be able to break it down into a sum of elements, each of which are killed by A prime power, right? So suppose that A is killed by R, and suppose that R has 2 relatively prime factors here, right? So do that. Right. Let me point out that everybody agree with that? I'll multiply that element of the module. So I've got A this way. Can anybody tell what the significance of this is?
Sure.
Okay, so A, now, what do you know about SXA? When you multiply by Y, what do you get? That's right, you get RA, which is 0. And what happens? And you multiply this by X, also 0, right? So in other words, here's the big takeaway. So what we have that if if R A equals 0, then A and R equals XY with GCD XY equals 1, then A is equal to alpha plus beta, where X alpha equals 0 and Y beta equals 0. Right? Everybody okay with that? So we can do induction here if you like, but So in general, in this case, right, and this is a torsion module, then there exists, and again, I'm gonna take A to be not zero because that's killed by everything and that bores me. Then there exists a R in R such that RA equals zero. Now I'm gonna go back again to the UFD part. R is equal to P1, A1, P2, A2, up to PK, AK. And notice the greatest common divisor of P1 to the A1 and the rest of the schmear is one. Everybody agree with that? And so we can proceed by induction. And so A can be written as alpha 1, alpha 2, plus alpha K with P1, A1, alpha 1 is 0, P2, A2, alpha 2 is 0, all the way down to PK, AK, alpha K is 0. Because these are relatively prime. We do need more than UFD here, but it was for this GCD business. Everybody see that? This establishes the first part because what we've shown is, hence, if A is in A, then A is in the sum of AP. Because each one of these alphas is killed by a power of a prime, right? In fact, this particular one is in AP1 up to AP. Right, okay with that? The rest of this is easier. That is, if the module is finitely generated, then there are only finitely many primes that you need, because every element that's a generator is contained in finitely many. So just take the collection of what contains all the generators and you're done there. Okay, any questions on that? All right, so everybody okay so far? Okay, so here's the next one. Theorem, theorem 13.1.8. Every finitely generated torsion module from PID can be written finitely generated torsion module M over a PID R can be written as a direct sum of MI where each MI is cyclic and is annihilated by some prime power e to the MI. So that is to say, MI is isomorphic to R mod PMI. I should call it PIMI. Okay. By the way, I do not claim that these, so this is some number of, this is basically isomorphic to R mod P1 to the M1, R mod P1 to the M2, and so forth. I don't claim that these PIs have to be distinct. You might have some repetition on some of them, right? But this follows from our previous work. So now let me give you the kind of the big structure theorem. And this hopefully is familiar, at least in some sense, to some of you. And I'll look at a couple of examples here.
What is a torsion? Like, I know what a torsion element is, but what is a torsion module?
It just means that every element of the module is a torsion element,
Oh.
has non-zero torsion. Okay, okay, so let's let A be a finitely generated module over a PID.
Dr. Cordino,
Yes,
if you have, let's say the, like, MI is, all of them are cyclic. But what if you have the MI of order 2? Is that contained in the MI of order 4 or no?
or you have all kinds of different things. I mean, under this blanket, you could have Z2, some Z2, some Z2. You could have Z2, some 4, some Z4, some Z7, some Z49. Just, you know, I mean, this is just basically a direct sum of R mod prime powers.
Sure.
That's all it is. And I can repeat them like I do here, you know, or not repeat them. Okay, so let's let A be a finitely generated module over PID. Let A be finitely generated over a PID. So I'm gonna give you two decompositions here. A is isomorphic to F sum AT, where F is free of finite rank. And AT is sum of a finite number of cyclic torsion modules. Number of cyclic torsion modules. These cyclic torsion modules, if any, are isomorphic to. So AT equals 0, or AT is isomorphic to R mod T1, direct sum R mod T1R, direct sum R mod T2R, direct sum R mod TKR. And these can be arranged such that T1 divides T2 all the way up to TK. T1 divides T2 divides TK. Right, and these TIs are called invariant factors. The rank of T, or I'm sorry, the rank of F and TIs determine A uniquely. And are uniquely determined by A. Right? This is called the invariant factor decomposition. You can also do it this way. AP can also be as a bunch of cyclic prime power modules. Into cyclic torsion modules. Each isomorphic to R mod P. R mod PIS by R. And again, I don't assume that the different PIs are different. The list of primes and the exponents are uniquely determined by A. So the primes P1 up to PK and exponents S1 up to SK are uniquely determined by A. And they are called, the set of elements PISI are called the elementary divisors. Now, I assume that all of you, although you may not have heard it exactly this terminology, have probably seen this. How many of you have seen these decompositions before? Okay. So some of you may not have seen. Let me give you some example with Z, because I'm a lazy man. But what's good for Z in this case, because this just generalizes what you have seen in the fundamental theorem of finitely generated Abelian groups. Let me give you an example. Suppose I give you this group here. And I'm going to give you a finite group over Z, because really the only thing that's of interest here is really the torsion part, because the free part is determined completely by the rank. It's just some number of copies of the ring R. How big the rank is, that's how many copies. End of story. So the torsion part's the easy part. So I'm going to look at an example just over Z, but you can replace Z by any PIDR. It's all the same here. It's all the same kind of idea. Let's suppose this is 47, direct sum Z 24, Z 25, Z 420, guess we want to celebrate, Z 84. Okay, so let's look at this here. I don't know about you all, but I've always wanted to know what the invariant factor and elementary divisor decompositions of this are. So let's kind of take this apart. the first thing I'm gonna do is I'm gonna rewrite this in what I hope is a sagacious manner. This is 49 times 3. This is 2 cubed times 3. This is 5 squared. This is 2 squared times 3 times 5 times 7. And this is 2 squared times 3 times 7. Everybody agree with my assessment here? Now, how many of you know this? The GCD are y'all aware of that? That's not too difficult to prove. And again, this is the old, it's because Z is a PID, so you can prove this in general. In fact, if this is any PID and you have two elements that are relatively prime, or mod AB is isomorphic to R mod A directs to mod B. Actually that's the Chinese remainder theorem is what that is. Everybody okay with that? This will allow me to break these down a little bit further. This is actually, I'm going to put these in parentheses so I can. Well, this one's a bear. Seven. Right, so. I've broken those down further, and now I'm kind of going to organize them. I'm going to go for invariant factor first, although I certainly don't have to, but I'm going to here, because I'm going to, I'm not invariant factor, I'm sorry, I'm going to do elementary divisor. Okay, so let's do the elementary divisor decomposition. Elementary divisor means that I organize these by prime powers. So let's see, the lowest power that I get is, well, I have powers of 2. There's a Z8. There's a Z4. There's a Z4. So I'm going to say this is Z8 direct sum Z4 direct sum Z4. So there's sort of my 2 torsion right there. By the way, this is the CeLO 2 subgroup of this group, right? Now I'm going to go through and suck out all my 3s here. I've got a singleton 3, singleton 3, singleton 3. So it looks like I just got 4 copies of Z3 here, right? Right. Looks like everything here. Let's see. The next prime it looks like is maybe 5. I've got a 25. I've got 5, and that's it. It looks like Z5. Oh, looks like I'm going top to bottom, 25 for X sums of 5. And it looks like the last player I have is times 7. And it looks like I've got a 49 and a pair of 7s. So there is my elementary divisor form. Actually, the previous line is really an elementary divisor form as well, because it's all broken up into prime powers. Right, it's just this is a little bit more organized where I've got my prime powers together. Everybody okay with them? Let me check here. 3, 7, 8, 10, 12. Yeah, that's right. You got a match there. Okay, how about invariant factor? Well, the invariant factor decomposition, there's a way that I can get that here. The difference here is for the invariant factors, I want these to be cyclic and I want these to be successively dividing. Actually, I'm going to divide the other way. I'm going to go from the biggest to the smallest. This is the way that you can get it. So you might ask yourself this, what is the largest cyclic subgroup of this? Be greedy. This put together with this, put together with this, put together with this. And I guess that's what, 600, so that's 294. I think that's right. 24 times 25 is 600. That should be, yeah, looks like 29,400. So basically it's Z49 cross C25 cross C3 cross C8. Everybody okay with that? So I've sort of plucked off the top here. Now go through and make the second biggest cyclic subgroup you can. 4 times 3 is 12, times 5 is 60, times 7 is 420. Third largest, 4 times 3 is 12, we're out of 5s, times 7 is 84. And the last piece, I'm out of everything except Z3s, so. There we go. This divides this, this divides this, this divides this. Everybody okay with that? And notice actually, so this is kind of nice also, with the invariant factor, the largest cyclic subgroup picks out your, this is the exponent of the group. So everything in this has order that divides 29,400, which may seem very large, but of course it's noticeably smaller than the order of the entire group, right? Everybody, how many of y'all have seen this before? The elementary divisor invariant factor kind of thing? Okay. And believe it or not, I'm not just doing this for fun because we're going to see a nice application of this with regard to canonical forms for matrices, as a matter of fact. Okay, so now that we've got this, we're going to use this as an application, this decomposition, as an application to, believe it or not, canonical forms for a matrix. So let's start off. And see. So let me start off. So this is section 13.2. decomposition of a linear transformation. Subtype of canonical forms. Well, at least some popular canonical forms. I'm sure there's others out there, but I'm gonna do some ones that will be of more importance perhaps. Definition. Let A, B. Okay, here, my notation here is I'm just mean n by n matrices over a field. Nothing in particular except they have to be square. They don't have to be invertible or anything. We say, A to B, if there exists, invertible P in MNF such that A equals PB P inverse. Some people lead with the P inverse, they conjugate with the P inverse BP. It makes absolutely no difference. Similarity is an equivalence relation, right? Note A is similar to B is an equivalence relation. Did they show that to you in 3110? I don't know if they do or not, but certainly it's true because A equals the identity, so A is similar to A. If A is similar to B, then A equals PB P inverse, which implies that B equals P inverse AP. And this is why the negative sign or the inverse sign doesn't make any difference. Right. And if A is similar to B and B is similar to C, then A equals PB P inverse and B equals QC Q inverse, where again, I'm just using the notation suggestively. The Q is also an invertible matrix. So this means that A equals P Q C Q inverse P inverse, right? Which is PQ C Q inverse P inverse, which is PQ C PQ inverse. Now, what does similarity do? Well, okay, since it's an equivalence relation, it basically takes all n by n matrices And it cuts them into equivalence classes, right? So you got all the invariant matrices. Now you can say two of them are similar if they're conjugate of each other, right? Somebody name an equivalence class that's only got one matrix in it. Can you identify it? Yeah, the identity matrix, I mean, look, if B is the identity matrix, what's gonna happen here, right? In fact, can you generalize that a little bit? Yes.
It's gonna be any matrix in the center of Mn.
Do you know what the center looks like? The centers are the scalar matrices, right? The diagonal's not good enough quite, but the scalar matrices are. That is a matrix that is basically just lambda times the identity. So, okay, so you've got all the scalar matrices are in equivalence class by themselves, so it looks like this is not doing much, right? But I'm gonna make this up at random, and I'm gonna have to be very unlucky for this not to work. Well, let's see here. Yeah, so. Complicated looking matrix, right? I mean, even though it's only 2 by 2, right, it does weird stuff, right? It takes the vector xy to the new vector 5x plus y minus x minus 4y, right? I mean, who knows what this does? However, everybody's favorite thing to do. So what do I get here? If I take the determinant of this, I get x squared minus 5x plus 4x is minus x. And that's going to be minus 20 plus 1 is minus 19. Okay, everybody okay so far? Now, on the eigenbase, if this equals 0, and I know it looks like this sucks, square root of 1 plus 76 over 2. So everybody agreed that I get 2 eigenvalues, right? I get, and they're both real. 1/2 plus radical 77 over 2 and 1/2 minus radical 77. So, can anybody tell me what's a consequence of the fact that I got 2 distinct eigenvalues? That's a. Who'd you have 3110 from? What? Who'd you have 3110 from? I had you. Rock and roll. Let's see, I just had to do a little commercial there. So I've got 2 distinct eigenvalues. That gives me, yes.
Isn't it a bit too late for anyone here?
But yeah, problem. Well, no, I did have 9,500 fall. Eigenvalues are this. There are 2 different ones, right? So I get 2 linearly independent eigenvectors, and by that problem that we had on last homework, that means that this matrix is diagonalizable. And what that means is actually this is similar to this matrix. Eigenvalues are that, so it should be 1/2 plus radical 77 over 2 and 1/2 minus radical 77 over 2. And that matrix, even though these entries kind of suck, it's a diagonal matrix and it's easier to deal with, right? So this thing right here has this thing in its equivalence class. And if I were doing computations, if I were trying to understand what this linear transformation is doing, I prefer this one. what it means for these matrices to be similar is you can pick a better basis for this. This is a matrix with respect to the standard basis does this. We can pick a different basis where it does this better. Basically, the basis consisting of the eigenvectors, right? And so canonical forms are very important for simplifying and doing better computations. And we're going to use this to find these equivalence classes in an efficient way. Yes.
Is, if you have a repeated eigenvalue,
Right.
is the problem that you have two different invertible matrices P that you could map, like your.
No, with a repeated eigenvalue, there's not enough information. Right, so a repeated eigenvalue, if you have a repeated eigenvalue, you can have a matrix that is diagonalizable or one that's not. Here's an easy example of a repeated eigenvalue. Is this, and this matrix is clearly diagonalizable, and the reason I know that is because it's diagonal. This, on the other hand, actually has a repeated eigenvalue, but is not diagonalized. Check the eigenvectors here, and you will only find one linearly independent. And try to do this definition here. Try to set up an invertible matrix to conjugate it to this, and it's impossible, right? And so when you know you've got a repeated eigenvalue, that's not enough information. You need to know a little bit more before you know if it's diagonalizable or not. Okay, other questions?